All right, good. Do I have to click got it? Yeah, okay. I consent to being recorded. Now, do I minimize?
No, you just share your screen.
Oh, okay. Can you all see that?
Nope.
Oh. So I have to share my screen again.
Yeah.
All right. Does that work?
That does work.
All right. So I'm Laurence Packer. I like bees. I've been studying them for nearly 50 years now, and I know I don't look old enough. So I've been studying the bees of the Atacama Desert on and off since 1998. And so it gives me pleasure to be able to talk to you about this today. You see, I'm trying to hide myself. There I am, I'm hidden. Okay, the deep tracks carved after centuries of intense movement of animals and people are lost in the distance to the south. The aridity of the landscape is absolute. Not a blade of vegetation exists for many miles around. That's a Google Translate version of Horacio Lauren's, one of his blog posts. I imagine it's even lovelier in Spanish. So this is the Inca Road that goes through parts of the absolute desert in northern Chile. So here's an outline of the talk. You know, what is the Atacama Desert? Why study bees there? There's far too much on this slide. You know, if I read all this out, I'd have run out of time. So anyway, this is what I'm going to be talking about. And this is, yeah, one of the great things about traveling to Chile is you can camp in really remote places, such as here. So arid areas are shown in orange, hyper-arid areas are shown in yellow. This is from Wikipedia, so we know it's right. And I'm going to be talking about both the hyper-arid areas and the areas higher up, just on the western slopes of the Andes, pretty much up to the border with Bolivia and Argentina, and to the north to the border of Peru. So some of these areas are technically just a bit outside what you might call the Atacama Desert. And I'm not including the southernmost parts. So on the left, we see some precipitation data for the southern part of South America. And it shows some idea that the kind of arid areas in Patagonia are to some extent joined up with those in Chile. But most of the, less than 100 millimeters, there's parts of the Atacama where people have never recorded rain. So we'll get to that in a minute. Here's a cross section. If you look at the top left, there's a yellow bar. This is the cross section schematic from there. So we've got the coastal Cordillera, which varies in altitude. The highest mountain there, actually, I think it's up to 3,000 meters. But it varies in height, in altitude, in different parts, north to south. The Central Depression, that's where most of the minerals got left behind, and where a lot of the mining is. And these areas are mostly hyper-arid. One definition of that is less than 2 millimeters of rain a year. And then we get arid areas up to, at this latitude, 20 degrees south, up to over 4,000 meters. There are some bees that you can get here over 4,000 meters, but not too many. And then above that, it's semi-arid. At that latitude, it varies as you go up and down. So it's been arid in places for 200 million years. The people, researchers into the age of deserts keep changing their mind as to what is the oldest desert in the world. And I think the Namib Desert probably does win, but there are, you can find statements that the Atacama is the oldest desert, and some parts of it seem to have been arid for about 200 million years. It's been hyper-arid for 3 million years or so. So, why look for bees where there's no chlorophyll? Well, there's biogeographic interest in this area, that, as there is for the whole country. It's isolated because to the left, you've got the water. To the right, you got these mountains. To the south, it gets very cold, and also you've got an ocean there. And then to the far north, it's extremely dry, so it's highly isolated. The mountains are still growing. In some parts of Chile, the mountains are growing at the rate of 30 centimeters or so a year. But that is a lot less than the peak of Andean orogeny about 13 to 15 million years ago. It was more than twice that. So some of the climatic data. Arica, if you get a drop of rain there, it's not going to rain for on average another year. Same pretty much for Iquique. If you get high up, it gets wetter. Caspana, 73 millimeters. Calama, which is in the central depression, that's less than 6. Potro Rios in the south, 44 millimeters. Driest place in the USA, Calexico, that's a rainforest in comparison to most of the Atacama Desert. Of course, it's not a rainforest, it's an arid desert. But we're talking about places that have 2 orders of magnitude less rain than the driest place in the USA. But even the spots shown on this map are pretty wet compared to here. Right in the middle of the hyperarid Atacama, we get this little place called Quijagua, where there is on average a 20th of a millimeter of rain a year. You know, just imagine being the local meteorologist and you come home. Was any water in your rain gauge today, dear? No, just the same as the last 27 bloody years then. Yes, so why is there anybody with a rain gauge here? And the reason is you can actually see in the this Google Earth image here, the Rio Loa, that's Chile's longest river, and it snakes its way through the Atacama Desert from the Andes on the right. And here it fans out. So as the water melts from the winter snows, you get a bit of fanning out of the surface water, and there is enough water there for, you know, maybe 20 or so people to eke out an agricultural existence, and presumably one of them has rain gauge. Okay, so if we plot this on a histogram, obviously this is one of those situations where if I was doing a proper job, the vertical axis would have been a logarithmic axis, but basically you can see here that the 3 northernmost cities don't score on such a scale. Santiago gets a bit more rain than anywhere else. Chañaral is about 1,000 kilometers north of Santiago and also on the coast. And from my point of view, that's where the real desert begins, although in reality, it's actually several hundred kilometers further south. So averages are pretty misleading. Here we see obviously a different place, Iquique, not the airport, because the airport has less rain, but here's another weather station in Iquique. The average is less than 2 millimeters of rain a year, but you might get a lot of rain one year, a little bit of rain the next, and then nothing at all for 12 years. And it's kind of known that in desert temperature variation, it can be quite extreme. So in the top left here, this is the Rio Loa, and these data are from just inland from its mouth here. And we can see that different spots in this, where this research was done, the temperature can get up to over 30. But it can get down to pretty cold at night. And this is in October. So this is late spring, early summer, I guess. Yeah, late spring. Not that that really means a great deal, I think, here. And the humidity varies in contrast to that. We can get up to 100% humidity. But then at night, it drops down to 20. So what about the habitats where we might find bees? Here's a list of the ones I'm going to show you a little bit of information about. Collecting along the roadsides is often more productive than anywhere else. as anybody that's traveled down to the B course in Arizona will know. You spend most of your time up by the side of roads. And here we see a little patch that had water in it. This is just south of Antofagasta. There's there's maybe 4 species of plants there. And I'm carrying a pan trap, or actually it's a deep cut trap, I call them, because they're kind of like this, that I'd left there 3 weeks earlier with propylene glycol in it, because it doesn't evaporate. And there's an undescribed species of bee from there. And, there was no vegetation for miles in any directions except here. There are some parts, the Atacama, where there is no seed bank. And so even if it does rain, as is evidenced here, you don't get anything growing. There are you can find statements that there are places in the Atacama where rain has never been recorded. But mining geologists tell me that on the tailings from the mines, you can find evidence that there must have been heavy rainfall at least once in the last 120 years in most of these areas. But in places, it's not enough to maintain a seed bank. This is the mouth of the Rio Loa. It is I believe it's the only river in the Atacama that actually makes it to the ocean. It's used a lot in agriculture higher up, and sometimes this area does flood, but this is it on an average. I can't remember what day or what the conditions have been here, but for most of its length, the longest river in Chile can be jumped over. I've put out traps here and not caught. In general, I've not found anything at all interesting along the river. Coastal fog areas are another matter. This is called the Camanchaca, and this is the main source of vegetation-inducing moisture up to about 1,200 meters in altitude. Above that, it gets too dry in at least some areas for it to persist. In other areas, it only gets up to about 800 meters or even less. It can be quite extensive, and as we'll see, we get some extreme examples of this here. So dotted along the coast of southern Peru and northern Chile, there are these fog oases. And in Peru, some of them are enormous. But in Chile, they're mostly small. And you get a fog oasis when there's a promontory that sticks out into the ocean, and the Humboldt Current is cold water, and the prevailing winds push the cold, damp air up over the promontory that sticks out into the ocean. And if there's a bay on the other side, where on the north or northeast area, there's another high area, then the fog pretty much gets trapped there. So this is the road to Alto Patache, which is Chile's largest fog oasis. And to get here, you've been driving for a couple of hours, where the only other living things you will see are other drivers or things that people have planted and kept watered. This is the wettest place I've ever been, except when I've been underwater. So you can see here it's fog, and the gentleman on the left there is Horacio Lorraine, who I gave a quotation of earlier, and he took me here. And just to the right, if you stood just off the right of here, there's a kind of vertical, not quite vertical, but there's a steep cliff, and you look towards the ocean and you can see nothing. You can't see the hand in front of your face. It is gale force fog, and water condenses on every hair on your body. So my eyelid, my eyebrows were raining. My nose was full of water. My beard was condensing water. And you can get 7.8 liters as an average if you put out a square meter of mesh. So it's a remarkable place. Like, you're in the middle of the world's driest desert, and you've been wetter than you ever have been before. But of course, if you put out traps with propylene glycol in them, you can catch some bees here. There were four in the most recent publication on the flora of this site I'm aware of. They found 42 species of plants. I think they've found a couple more since then. Oases are another area where you can get bees. Here is a fruit and vegetable producing town called Pica. And I guess again, you're in the middle of dust and you've got this agricultural area. And so the geological conditions here must be such that the water table gets close to the surface, and the water comes from meltwater from the Andes Mountains to the east. San Pedro de Atacama is a famous place, I think. And it used to be a lot wetter than it is now. This is another oasis town. There's an indigenous community of 1,000 people here, which on an average day is exceeded by the number of tourists. Here's Pedro De Valdivia's house that's 480 years old. Doesn't look to be in very good condition. In the hills around there, you get these large cacti, and the roof of the church is made up of wood from these. And it's really rather spectacularly beautiful. So the local indigenous knowledge I've got is from this man here, Orlando Umire Coca. He's running a brewery here, and my wife and I helped him for a day grinding up the ingredients. He says that, in the past, this area was marshy. It isn't marshy anymore. And then there's a forest in the middle of the desert. You can see on the horizon there. So again, you've been driving through areas where there's, the only trees are ones that have been planted and watered to keep them alive by people. And you've been driving like that for like 700 kilometers. And all of a sudden you're in this. This is the Pampa de Tamarugales in northern Chile. And it is remarkable. Like you've been driving through bone dry areas, and then you stop here and there's birds singing and butterflies flitting around. It's just spectacular. The soil is of a nature where you pick up a lump of this and you hit it and it rings like pottery because it's baked. So this was a much larger forested area, and it was a forest because again, the geological conditions mean that the water table is reasonably close to the surface. And the tamarugo trees, their seeds, after a heavy rain, they germinate as quickly as possible and put their roots down as quickly as possible. If they reach the water table, then the tree survives. If they don't, then it dies out. As a result of burning wood for the various mines in the Atacama Desert, the woodland was threatened, and it's the first national park in Chile, but you can see that most of the trees have been planted. They're in nice little rows, but there are a couple of areas where the original woodland is left as it was. High altitude gets wetter as you go higher up. Here we see from quite a large area on the western slopes of the Andes over altitudes from 2,000 to 3,200 meters. These are the 4 sites that people did transects of counting the number of plant species from the absolute desert, where by definition there is no vegetation. And so we go from 0 up to 25 or so. And these are just the desert adapted plants. So they're not looking at high altitude plants. They're just looking at the species that are adapted to very dry conditions. Just to prove I actually have been there, that's a Geretta. It's an umbellifer, so it's related to carrots. People, it looks nice and soft, doesn't it? But you can attack it with an axe and burn it. And people did that, again, to keep warm and to cook food. in the mining towns lower down. It's pollinated by, I think, mostly flies. The flowers are tiny, tiny little yellow things. And so it can get really quite moist at high altitude, especially in the Altiplano. And you get these bofedalas, which are kind of high Andean marshlands. Okay, so now to talk about extreme events. This shows annual rainfall in Antofagasta over 30 years. And we can see that the wettest year, whatever this was, the bottom has gone off my screen, but sometime in the 70s, it got 17 millimeters in the year. In March 2015, in 24 hours, it got more than that, which is remarkable. So I had to go there. This is what it looked like in April. You can see that somebody had gone for a walk, and they'd come back taking a slightly different path. I'm not sure why the vegetation grew in their footprints as a result of that's where the seeds were, or that's where the water in the rain collected. Nonetheless, this is pretty interesting. This is what it looked like in May. It looks like Canada in February, but the snow is actually Nolana. There are two species of Nolana growing here. Mike Dillon told me what they were, but I've forgotten. And you can see these tracks. And so people, this is about 8 kilometers from the city center. And the people were so unused to there being vegetation on the hills that it became a picnic event. People will come up here, maybe stay the weekend, because, being somewhere this green was an extremely rare event. What was even rarer was that in August, it rained more than over 2 days than you got in any whole year in the going back to the 1970, and so the total amount of rain that year then approximately almost 40 millimeters. And so normally what happens with vegetation here is that after rain, things will germinate, grow quickly, and they're dead and dried within 6 weeks or so. Here, the same plants that were around that were germinating in March were still going in October because of this double rainfall. These ones do look kind of deadish, but there were flowers around. Another extreme event, Palo Buque. This is the first time this hillside had been green in at least 35 years, because Horacio Larraín, who at the time, he was 82, I think, when this happened, he was living in Iquique, and whenever anything particularly unusual happened, he would drive there and ask people, okay, have you ever seen this? And the oldest person he found, or the person that had been living there the longest, has been living there for 35 years. And he said, nope, it's never been green. So I climbed up to this for 5 hours. The car is there. It's a little tiny white speck. And I caught 3 bees. One of them's undescribed. Okay. So one point of interest to me in the northern Atacama is shown here. So you've got this summer-winter rainfall boundary, which is approximately this diagonal. And to the north and east of this line, rainfall, if you get it, is mostly in summer. Right, so that's going to be January, February, and March down there, which is what we can see in this histogram for Caspana, which is shown in the red star. Padre Rios, further south, gets most of its rain in summer, May, June, July, and August. So this is a map. Okay, so we've got altitude on, funnily enough, the vertical axis. That's useful. On the horizontal axis, we got degrees latitude, and these are the different habitats that you get shown in 2 dimensions. And so we can see that the disjunction between the winter and summer rainfall areas occurs at about 24.5 degrees south, which is where the lower vegetation limit, super dry conditions, reaches furthest inland. That's over 3,000 meters of pretty much no vegetation around here. But to the north of that area, rainfall, if you get it, is mostly in summer. To the south, rainfall, if you get it, is mostly in winter. So here we see a map of the whole of South America, pretty much, with the percent of all precipitation during the year that comes in December, January, February, March. So this is the summer rainfall, and we can see that the extreme north of Chile gets nearly all of its rainfall in the summer. The south of Chile gets almost no rainfall in the summer. Okay, so we'll get back to that because I'm going to be looking at the effect that might have had on bee diversity. Field methods: I arrived in Santiago, I rent a vehicle, I go to Alfredo Ugarte's house, and we're in the museum that was started by his uncle, Lucho Peña. That's where I store a lot of my stuff. Thank you, Alfredo. And then drive off into the middle of nowhere. Accommodation costs are quite affordable. I don't need a rain fly for my tent most of the time. And so that's fairly easy. Breaking down in the middle of the world's driest desert can be a little worrying. It was a long walk to the nearest road where people were likely to be going by more than once or twice a day. Actually, I think all day I saw 2 vehicles on this road. This was in the good old days of when, if you wanted to do genetic analyses, you needed liquid nitrogen. So this is a liquid nitrogen container, and that's a water tank. So you drive around, they exaggerate a bit on the road signs there. This is indicating you're going uphill. And then if you see a sign like this, you know you're in Argentina and you have to turn back. Intensive pan trapping. Find an interesting bee, blanket the ground with pan traps. There's lots of them here. And I'm in search for one particular species, which after all of this, I think I got a total of 6 specimens. Another nice thing about pan traps is you can use them for breakfast. So this is the campsite in the Pampa de Tamarugal, is a national park. Okay, so one of the problems with doing biodiversity surveys in a formal way is that, or assessing specimens from museum records, is that the sampling is not random. So we made an attempt. 2 students of mine, James Postlethwaite and Spencer Monkton, spent 8 months in Chile in 2013, and they put 5 altitudinal transects, each with 8 sites that, where possible, was separated by 500 meters in altitude, not driving distance. And so we can see their collecting sites on this map here. So I've collected in other parts of Chile also. I'm only going to be talking about areas north of 28 degrees south here in my talk. But here's some of the results. We got more bees than at the time I had space to store. It's taken a long time. Like, I first started this in 1998, made a small collection that got all pinned relatively promptly. But when you start running, 84,000 pan trap days, you pretty much run out of space and time. I reckon that all of the sorting, pinning, and labeling is about 95% complete, and that 95% complete includes things identified to genus. 30 new species from all this have been described, some of them by other people, and I've got at least 50 more species to describe. The 2 main genera that I still need to work on are, funnily enough, Megachile and, well, funnily enough, Lasioglossum. Okay, so the material I'm going to be talking about are the ones that have been barcoded and or revised, plus a couple of other interesting things. So much of the rest of the talk is going to be preliminary. So here's a map of localities where we've got barcoded material. And, I just prepared this yesterday, and it's interesting when you put all your data on a map like this, because it shows you areas where you have to go. And some of these large areas, such as here, and there is a road that goes in here. It's not a very good one, and it's really long, to get through the absolute desert where there's no vegetation to try and find somewhere where there might be plants. But clearly there are some areas that I need to get to if it's at all possible at some point in the future. I'm probably too old. I should send somebody younger. Number of species divided into 2 degrees latitude. So, the most in the south, that's not particularly surprising. It is a little wetter in the extreme north where I've got, it might tell me if I put the, no, it doesn't tell me. So this is about getting over 65 species, I think. Fewer here and here. This is where the absolute desert gets closest to the highest altitude. So you wouldn't expect so many species there, but we have found new species. I should mention that in some of these places, the particularly difficult of access places, I've left vein traps out with propylene glycol in them, sometimes for over a year. And I've caught, in areas where there's almost no vegetation, it's really just about the only efficient way of collecting. And I've described 2 new species as a result of traps left out for long periods of time way up in the mountains here. Here's the percent of species undescribed at the time of collection. Almost over half of them in some areas. The total percent of new species through this area, and I forgot to mention here, the total number of species is 204. So in the whatever it is, over 10,000 square kilometers of the Atacama Desert, there's about as many species of bees as Mike Sharkey gets in a square meter of Costa Rica. For those of you that saw his talk some time ago now. But a lot of them are all, maybe the proportion undescribed isn't as high as for him. But for bees, finding an area where over half the species haven't been described is pretty interesting. Okay, so now I'm going to talk about what's going on with this summer-winter rainfall disjunction. There's James Postlethwaite. Back behind him, there is Spencer Monkton. These are the people that did the sampling along those transects I showed you earlier. And James found that there are 3 genera he dealt with in his thesis. And they all had species that seemed to show that the closest relative of the one in the summer rainfall area in the top right of these diagrams, the closest relatives of these were from the winter rainfall area. The problem with, it's still true in Neophydelia when you do it phylogenetically, but the problem with the 2 panels on the right, Callanicium and Cyanohalictus, is that, what about Bolivia, Peru, and Argentina? Right? So you can't say that this winter-summer rainfall disjunction played a role in speciation of these bees because we don't have data from Peru, Bolivia, and Argentina. Maybe their closest relatives are over a political border in countries where it's much more difficult or absolutely impossible to get permits to collect specimens. This isn't true in Neophydelia. We do have the species shown in blue here from Peru now, but it's very close to the border, so the same pattern holds. So the origin of this winter-summer rainfall disjunction probably did play a role in the evolution of Neophydelia diversity. We do have a couple of complete phylogenies for all of the species in a taxonomic group. This is Spencer Monkton's thesis work, and we can see here that there is 1 species in the subgenus Heterodicilis, which is found to the top and the right of the blue diagonal that shows the approximate difference between the summer and winter rainfall areas. And its sister group is 2 species that are found further south in the winter rainfall area. So this is evidence that this disjunction might have played a role, as is this, which is from Gonzalez et al.'s revision of the genus Spinoliella. And there's this beautifully named Spinoliella packeri that is found only in the winter rainfall, summer rainfall area, and its closest relative is found to the south. So these are quite different, but sister species, one on one side of this divide and one on the other. So now I'm going to talk about larger scale phylogenetic analysis. Again, these results are preliminary and they're based upon just a few nuclear genes for a whole subfamily of bees. And so here we see the time-calibrated phylogeny for the various species which we had specimens for which we could get DNA from. And it's believed that the disjunction between the summer and winter rainfall areas arose when permanent El Nino conditions ceased. So El Nino brings, from your point of view, but El Nino brings in wet conditions into the desert from the coast. La Nina conditions bring in the moisture from the other side of the Andes over into the high altitudes in the northeast. And it was a permanent El Nino for some time before 2 million years ago, probably going back to 20 or 30, as old as the Andes are, extremely high. And so here we see the vertical bar is 2 million years or so ago, and each of these stars denotes a situation where on one side of the node, that phylogenetic node that's hidden by the vertical line, on one side we've got a species that are found only in the winter rainfall area, and another one that's only found in the summer rainfall area. The same thing happens down here and down here. And so we've got 3 of the 4 examples where we've got winter rainfall taxon on one side of the node and a summer rainfall taxon on the other side of the node. In 3 of the 4 cases where that pattern is shown in the phylogeny, the dating, very preliminary dating, suggests that 3 of the examples fit right on what you might expect if the development of this northeastern summer rainfall area had a role in the evolution of these bees. Now, that's for where we've got all of the data necessary to do a dated phylogeny, which means, the ones for which we've got decent DNA data, which at the time we did that, and that was Eduardo Almeida and Jennifer Albert helped me with those because I'm not a DNA person by any stretch of the imagination. Now it's possible to get DNA for thousands of loci out of a specimen that's been sitting around in a museum for 100 years. And so we are now, with Michael Brandstetter in Utah, working on all of these species. But this shows the phylogeny for one genus with all the Chilean ones shown. And the red ones are in summer rainfall areas, the green ones are in winter rainfall areas, and this suggests there have been 13 transitions from one to the other in the genus. The geography is mapped on here parsimoniously. So this is a lot of diversification on either side of this environmental barrier. Now, 4 of these pairs of species are barely distinguishable. Some of them might, I don't believe in subspecies. Some of them might not be true species. I've not looked in, we're getting more data as I speak to investigate this. But in some cases, they're definitely different. but very, very similar to each other, suggesting really very recent divergence. So what has been the environmental history of this area? That gets us to pack rat middens and a whole bunch of other things, but it's more fun talking about pack rat middens than it is any of the other types of data that give us information about when things happened. So pack rats are cute. One of the great things about them is that they live in a midden that is made up of vegetation, their own urine and feces, and they last, one of the data points I'll show you in a minute is from a midden over 40,000 years old. So you can go in there and you can find out what they've been eating. And as they forage for at most about 500 meters from their nest, from their midden, you can tell what the vegetation was like at the time the midden was formed. And using radiocarbon dating, you can find out exactly when that midden had been put there. Some of them get quite enormous, as you can see here. Some of them are more the size of a football. So these are seeds from a 17,000-year-old midden. And these seeds look like you could plant them and germinate them like next week. It's pretty amazing. And so people have used all sorts of, radiocarbon. You can get pollen from the middens. All sorts of data have been used from pack rat middens to try and work out what's going on with the geography and environment, the environment of the past in Chile. So here we see, this is at the bottom, we got a midden that's almost 45,000 years old. The verticals are the different plants. And this shows us then that there was this wet period with a lot of these pre-Puna taxa in this period, 16 to 10,000 years ago. And the fact that there had been wetter periods in the past is well established. But what these data also show is these are the conditions as they are now. The red dots show the study sites where they got middens, and then we've got steppe and snowy areas in yellow and blue. We've got the absolute desert in orange, and this is where things are now. And we can see that currently these sites are all in the absolute desert, no vegetation except the one at the top, which is on the edge between absolute desert and steppe vegetation. But 16,000 years ago, everything galloped downhill up to about 1,000 meters. It was wetter, and so we've got steppe vegetation, and the absolute desert is restricted to just these two tiny areas. This isn't the coast. This is just the map that I think it was Claudio Latour sent me. So we can see that at the time these middens were formed, there was steppe vegetation, and that is indicated by the seeds that they find in the middens. So it would take a whole thesis, I think, to sort this one out. But what I've done here, so James, as part of his thesis, he amalgamated about the data from about 8 different studies and plotted whether, at different times, the data from all sorts of different types of information, erosion, deposition, pollen, middens, etc. And so the data were chaotic. So I've arranged them and added, not all, but some of the more recent papers on the subject. And here we got degrees south. So I've arranged them from north to south, from 20 degrees down to 26. And this is thousands of years ago, so 1 to 20. So we can see that even nearby sites are suggesting quite different. One here showing it's drier, one here showing it's wetter. Maybe there's an altitude difference in the study sites. I've not looked into that. But here are the two well-known moisture area times since the last glacial peaks. Maximum the glaciers about 15, 16,000 years ago. So there were two distinct wet periods with a short dry period in the middle, but even not all the data here suggests this. But then if we go further back into time, it was wetter down here over, and the numbers here show the time frame. So, you know, wetter from 100 to 130,000 years ago, wetter from 35 to 80,000 years ago at 21 degrees south. So what I think's going on, right? So this is short time periods, right? So we had a lot wetter periods, you know, up to about 10,000 years ago for sure. And what I think happened then is that in some of these situations, we had the wetter uphill species moving downhill. And then as conditions dried out again, with the recession of the glaciers, leaving populations behind that might have been captured by the winter rainfall area, and the converse, as the winter rains get higher up into the mountains, maybe some of the northeastern species populations are captured, and that gives us some of these things here. But the data seem to suggest that more capture of northeastern ones has happened by the drier southwestern habitats, perhaps as a result of the vegetation galloping downhill for 1,000 meters. Okay, so somebody tell me if you want me to stop. I've got 8 minutes left, and I've got a couple of stories. If you want me to go for the full hour, what do you reckon?
Go for it.
All right, so a few more stories. So some of the places I've put out traps are the kind of places that no biologist will want to spend much time there, because you wouldn't find any organisms, such as here, Tocopilla. It's a coastal town. You know, fishing and mining are the industries here. That's why there are people that live there. But there's this canyon through which a road runs, and the fog collects along here and the little side canyons. And so there is some vegetation, and I put out traps here. I've caught a total of 7 species. 4 of them are undescribed. Still, 2 of them have been described. One was I described already, and another one is known from much wider range, was previously described. 2 of these species aren't known from anywhere else, even though I've collected other coastal areas to the north and south. Palobuque, the place I showed you earlier, just south of Iquique. Remember I said I caught 3 bees? Well, 2 of them are an undescribed species, and it's unknown from anywhere else. The other one is one of these Phainoleucus. You get them everywhere. Like, these bees seem to cope in almost any environment. Maybe because they're communal with females sharing a nest entrance. I guess that, we don't know that, but the relatives of it are. And then that area where I showed you where it looked like it had snowed, northeast of Antofagasta. All of the species I caught there were undescribed at the time I collected them. 2 have since been collected. 2 of them are 2 of the undescribed ones aren't known from anywhere else. And then all of them were found both in May and October, except for 2 species in Parasaurus, where one is only found after the summer rains, and the other one was only found after the winter rains. We've got genetic evidence suggesting that these actually are not the same thing, and we're working on the morphology of those with my technician, Liam Graham. This is a new genus that I found, a single specimen in a trap that had been left out for 3 or 4 weeks near the town of Maminia. When I caught it, you know, just eyeballing it, it was obviously different. There's lots, you know, there's a very abundant undescribed species of Liphanthus, which is an andrenid, that looks just like this. But this is about twice the size. So when I saw it in the trap, I thought, well, that's the largest Liphanthus I've ever seen. When I got it home, I couldn't work out what family it belonged to for a while. It is a long-tongued bee, although this doesn't look to be a very long tongue, and neither does this. And for bee nerds, which I imagine most of you are, unlike just about every other long-tongued bee, it doesn't have a glossal rod, something to give the tongue some strength. So this is a short-tongued Fidelia and a short-tongued megachilid. It's separated from its sister group, Neophidelia, that I talked about a bit earlier, over 30 million years ago, which is before the Andes got tall enough to help create, oh, it doesn't say, hyperarid conditions in the Atacama Desert. So this single specimen, I've blasted the whole area with pan traps for multiple years since collecting that one. Not another specimen has shown up. And so this single specimen is indicative of 30 million years of evolution with nothing else to fall in. You know, I looked at the pollen on the bee. I think there was like 10 different types of pollen grains on it, but it had almost no pollen in the scopa anyway. And so, you know, most of that is likely from the liquid in the pan trap rather than being been out collecting. So I don't even know what plants to look on for it. And then lastly, we've got these super long-tongued bees. This is the bee I just mentioned as having been described before. It's one of the most common and widespread bees in the damper parts of the Atacama Desert, pretty much wherever you get the larger flowered nolanas. It's got a really long tongue. This is Geodicilus longiceps that was caught on flowers of Tequilia right on the edge of the absolute desert. It was literally on the last patch of plants driving down from the mountains towards an area where there was no vegetation. Note that these two bees look superficially very similar. They are in the same subfamily, but they're different genera. This one gets its long tongue primarily from the maxillary palps, which is shown here. In contrast, the maxillary palps of this one are tiny. Right, so this is the apex of the glossa on this bee. You know, these are technically short-tongued bees, they're collidids. So this is the apex of the, this is the apex, where's my pointer gun? This is the apex of the glossa on this one. The apex of the glossa on this one is here. So these bees have found different ways of getting to the deep nectaries of desert plants. Now, if you're a plant in the desert, you don't want to have your nectar in a shallow bowl. It'll be evaporated before you produced it. So many of desert bees have their nectaries really deep, as we can see here. So this is a different species of Xera melissa from Rosen and Wyman. And so we can see, you know, it's got its head stuck. It can't get down to the nectaries down here, but it's got this long mouth part with the long maxillary palps at the end. And this is Xera melissa rosini. It's the only bee I know. It's got some long-tongued relatives in the same clade. They're all undescribed, but none of them have got this groove on the underside of the thorax with bristles to hold the tongue in place so it doesn't drool while it's flying. So I've got to thank all sorts of people for funding, camera equipment, taking the pictures and helping me with making the collections. And I thank you for your attention.
Thank you, Laurence. So are there any questions? You can either put them in the chat or you can unmute yourself and just ask Laurence. One question I had is that resources are extremely unpredictable. Do you have any sense how long a bee can exist as a larva or a pre-pupa and wait for resources to become available, or even as adults in a quiescent state? Is it potentially decades?
I don't know of any examples of that lasting decades, but at least I think 7 years. Jerry Rosen had the fully grown larva of a Neophidelia in his drawer in the American Museum of Natural History. And I think at the time he told me about it, it had been there for 7 years and was still alive. When I asked him about what had happened to it, I don't think he could remember. I brought back a dead Nolana stem with a bee nest in it on one of my earlier trips to Chile. And after 3 years of waiting for something to emerge, I lost my patience. And so I was keeping them in a glass vial. I unscrewed the vial and breathed into it once every 3 weeks for 2 months. So after the third example of me breathing into it, the bees must have thought, in inverted commas, it's humid enough for there to be resources out there for me. I'm going to fly around now, and I got one of the Heterodicylus that Spencer Monkton studied in his thesis. But that was 3 years, and it was still alive. And I don't, maybe it had already been there for a year when I picked the twig. So they can last for 7 or so years. I think that the seed bank in the desert can last for decades and decades. I'm not so sure bees can last quite that long.
Well, yeah, because I guess the other way to look at it is if you look at the rainfall patterns, it seems like that would tell you how long at least a bee would have to last to get, to be able to take advantages of these resources that are extremely intermittent.
Yeah, and unfortunately, most of the weather data come from places which are wetter on average. I guess Quijagua might be an exception, but there's groundwater, and so that makes things completely different. I think there are probably areas where there hasn't been vegetation for 10 years or more where I've caught bees, but because of the lack of weather stations in the middle of nowhere where nobody lives, it's difficult to be so certain of that. I guess with satellite imagery and weather estimation, you can get more accurate information on that these days, but I'm not aware of stuff at a fine enough scale for that to be useful to me.
And then one last question is, and you may have mentioned this, but when you do see an abundance of resources, do you see an abundance of pollinators? Are there times where you've seen lots of flowers and no bees, or the opposite?
I've certainly seen situations where there's lots of flowers and almost no bees. Now, the problem with that, of course, is if you've got a meadow in an area where there's usually not many flowers, bee density is going to be low, and finding bees is going to be difficult, even if there's reasonable numbers there. And that applies also if you're trapping. But certainly, I've seen. And it seems to be temporarily constrained in that, for example, some places along the coast within the area I'm talking about, you can see a really beautiful, diverse meadow of flowers after a good rain. And, finding bees is not easy for some weeks, whereas before that time and after that time, it can be quite good. So there's a lot of, I think, fine scale nuance here that we don't have data to address because I've not kept track of you've seen the distances over which I'm traveling. I'm on an average trip, I'm driving over 10,000 kilometers in 3 weeks. So I'm not collecting lots of data at each place. I'm just putting out traps in the morning. Or at any time of day, actually, because I'll leave them there for weeks, and then collecting during the day when it's warm enough for the bees to be out, and then driving on to the next spot, sometimes hundreds of kilometers away. So I've not collected as much floral data as your average ecologist would have wanted me to.
Okay, thanks.
Laurence, what happens when you leave vein traps out for a year?
Depends where you leave them. I've had problems with them. So these are the spring star ones, and the blue ones are much better than the yellow ones. And the weak point is the funnel, the part of the funnel that you screw in. That seems to degrade in the sunlight, and as a lot of the areas where I worked are really windy, the veins get blown away, the top gets blown away. I dig them into the ground, and so at one point I did find the bucket with propylene glycol and lazy glossum and nothing else. This is one of the river sites I mentioned where I don't get much. So that's a bit disappointing. Once I left a trap out and forgot about it. And then driving around the same area, I thought to myself, this is a good spot. And I got out and found a vein trap that had been knocked over. It had two dead rodents, or it had fallen over, probably as a result of the snow. It had two dead rodents in it. And so sorting the bees out from that was quite unpleasant. But they do dry out a bit. You don't want to put them out where it's going to rain or snow a lot, but in the Atacama, that's rarely an issue. With these extreme rainfall events that they've been happening. And I didn't mention that, like everywhere else, these are getting, extreme conditions are getting more common. Like once in 100 years, floods are happening every 5 years sometimes. So you get a soup. The bees are often, the wings shrivel, but they're usually identifiable. I've left pan traps out for 3 weeks, and even ones that have been run over by a car, completely shattered, there are identifiable bees in amongst the dust at the bottom.
Oh, wow. And then how's the DNA when you go back to it?
Well, there's been no studies of this, as far as I'm aware, of the impact of different durations of storage in propylene glycol. Christopher, for the molecular phylogeny of the Fidelia, Christopher Prats did manage to get 6 or 7 nuclear genes from the one specimen. What I did was I took the head and most of the, often the propleura, the front legs, prosternum come off, leaving the pronotum in a big hole for you to be able to put tweezers in and get the thoracic musculature out. So I did that and sent it to him. And he's since got, I don't know how many UCE loci from the same sample. But, for all I know, that bee had fallen into the trap the day before I picked it up. But it was in propylene glycol until I got it home. So it had been in propylene glycol for at least 2 weeks.
Cool. Thank you.
You're welcome. Good to see you.
Yeah, good to see you, Laurence. Always good to hear your thoughts.
All right.
If there are no more questions, then because we are 8 minutes past the hour, I will stop the recording and say thanks a lot, Laurence. That was a great talk.
Thank you very much.